Okay guys, so welcome back. So now we're going to try to solve a problem again for a closed system. So this is a type of piston cylinder assembly, but what is different from the other problem is that it has a set of stops over here. Okay, so what does that mean? Is that the piston, as you hit the piston, this is free to move up to the point when it's going to touch the stops. So up to this point until it gets to the stops, you can say that this process is constant pressure, because as the gas or the water here expands, this will move up, so the pressure will be constant inside. Okay, so that would be my first observation just by looking at this problem. But let us read the problem statement and see what is going on. So water contained in a piston cylinder assembly, initially at 1.5 bar and a quality of 20%, is heated at constant pressure, so that's what we just mentioned, until the piston hits the stops. Heating then continues until the water is saturated vapor. Show the process on a TV diagram and evaluate the work and heat transfer in kilojoules per kilogram for the whole process. Kinetic and potential energy can be neglected. Okay. So following the general procedure, so the first thing, let us read the problem statement again. So water contained in a piston cylinder assembly. So basically what I need to do is to just redo the figure over here. Alright, so this is water. Initially at 1.5 bar and a quality factor of 20%. Okay. In the problem, they ask us to do the TV diagram, so let's try to do everything at the same time. Okay, so if you remember, TV diagrams will always be of this form over here. And since this is a TV diagram, we know we are always going to go through lines of constant pressure. So let's see. What do we know? Initially, the pressure is 1.5 bar. So all this line is 1.5 bar. Okay. So state 1 would be located, let's say, over here, because we know x1 equal to 20%. So basically that means that it's 20% of gas and 80% of liquid. And you get here would be 100% of gas. So alright, so maybe we need this. So this value here would be V fluid, and this would be V gas. So let's see what's happening over here. So we are heating this. Okay, so an equality of 20 is heated at constant pressure. So basically you move along this line, so the piston moves freely up until it hits the brakes. So let's say it hits the brakes over here. Alright, we need to check this, but let's just assume this initially. So we go from here and now it hits the brakes. So now what's going to happen? At this point, what we can say is what? Is that V2 will be equal to whatever is the last process, because this will not be able to expand, so the volume will be constant. So we know that we'll be moving along this line over here. And we know that the heating continues until the water becomes saturated vapor. So this is the line of saturated vapor. So this is 3. Okay, so basically this is a process. We go from 1 to 2 to 2 to 3. So you can say that between 1 and 2 is a constant pressure. and between 2 and 3 is a constant volume. So you see that there is no way to solve this type of problem unless we have the figure. All right? So let's try to break this problem into two parts. So, all right, first, what do we need to solve? We know that we can neglect kinetic and potential energy, and that we need to solve for the work per unit mass and the heat per unit mass for the whole process. All right, so let us try to simplify this problem. First thing we can do maybe is to see what's happening in the process 1, 2, and then we can move to process 2 and 3. So, okay, so the first thing we can do is to find actually V1. So how can we find V1? We know this is equal to 1.5 bar. So that means that for water, we can go to table A5. And we know the pressure is 1.5 bars, which is the same as 150 kilopascals, because 1 bar is 100 kilopascals. All right, so now we can see here the figure on the table. At 150, let me try to zoom in. At 150 kilopascals, Vg is 1.1594 and Vg is 0.001053. Okay, so we can just write down at these pressures over here. We have that V fluid is equal to 0.001053 and that Vg is equal to 1.1594. Okay, so now using the relation V1 that should be on the table equal to V fluid plus X1, V gas minus V fluid, what do we get? So V fluid is 0.001053 plus X1 is 20% or 0.2. V gas is 1.1594 minus 0.001053. So if we do this calculation, we obtain that V1 is equal to 0.2327 cubic meters per kilogram. Okay, so now what we need to do is to try to find V2. So in order to do that, maybe we don't have to forget some information that was given on the figure, is that those two distances over here, let's call this one L1 and this one L2, and we know that L1 is equal to 0.05 meters and L2 will be equal to 0.03 meters. Okay. All right, so let me just redo a quick figure over here. The stop is over here. We can put our piston over here. And we know this will be the distance L1. This would be the distance L2. Okay? And let's say the cross-sectional area of this piston is A. So, by doing so, what will be the volume V1 equal to? Volume V1 will be the cross-sectional area of the piston times L1. Then we know that the specific volume is simply volume divided by mass. Okay? And this L here will be actually L1. Now we do something similar for V2, so at the stops. That would be equal to what? A times the total height. That would be L1 plus L2. And we know that the specific volume V2 is just volume divided by mass. So using these two relations over here, we can say that let's say V2 over V1 will be equal to what? Will be equal to A L1 plus L2 over M divided by A L1 over M. So this will simplify to what? The M will cancel out, the A will cancel out, and we'll have L1 plus L2 divided by L1. So basically at the end, we are left with V2 over V1 equal to L1 plus L2 over L1. So we know L1, we know L2, we know V1. So we can just say that V2 will be equal to L1 plus L2 over L1 times V1. So if we do the numerical application, we get V2 will be equal to what? So V1 was equal to 0.05 plus 0.03 divided by 0.05 times V1 that we just found to be equal to 0.2327. And if you do this calculation, you find that V2 is going to be equal to 0.3724 cubic meters per kilogram. Okay. All right. So let's go to the next page. All right, so now remember that the pressure between 1 and 2 is constant, okay, from the figure. So by definition, we know that the work is equal to P the volume, okay, and we know specific volume is volume over mass, so we could replace volume by mv, okay, but we know that the mass is constant, so this expression here becomes what? Work equal to Pd of mv, or this would just become work equal m integral of Pdv, or work over mass equals integral of P dV. So for process 1 and 2, we go from 1 and 2, we know pressure is constant and is equal to what? 150 kilopascals, and we go between V1 and V2. So we can say that the work 1,2 per unit mass will be equal to P V2 minus V1, where P will be P1. So that if we do the numerical application, we have work 1,2 over mass equal to 150 kilopascals times V2 we found to be equal to 0.3724 minus V1 was equal to 0.2327. So that is equal to 20.95 kilojoules per kilogram. Okay, so that will be the work between 1 and 2. Alright, so we found the work. Now we need to find what would be the heat transfer between 1 and 2. So in order to do that, we're going to use the first principle of thermodynamics, which is heat minus work equal to change in internal energy plus change in kinetic energy plus change in potential energy. In this problem, we can neglect the kinetic and the potential energy. So we're left with what? Q12 minus work 12 equal to the change in internal energy between 1 and 2. And we know this is equal to Q12 minus work 12 equals to M U2 minus U1. Or this would be Q12 over M minus work 12 over M equal to U2 minus U1. Or what we're trying to find, Q12 over M will be equal to U2 minus U1 plus work 12 over M. Okay, so in this equation we know this term that is equal to the 20.95. So we need to find what is U2 and what is U1. Okay? So I think I'm going to do that on a different video so that this video is not too long. So please, after this video, look at part 2.